Sit still for a moment, as still as you can manage. Feel the chair beneath you, the small pressure of your weight settling into the cushion, the quiet of the room, the steadiness of the floor. There is no wind on your face. Nothing on the shelf is trembling. The lamp is not swinging. By every measure your body is willing to make, you are exactly where you were a second ago, and a second before that, and a second before that. You are not moving. That sentence is the comfortable lie, because right now, without your permission, without the slightest sensation to warn you, you are travelling at roughly 370 kilometres every second through the only reference frame the universe has been generous enough to offer us, not per hour, per second. In the time it takes to read this sentence aloud, you and your chair and your quiet room have been carried farther than the distance from London to New York. And that number, 370, is not even the whole picture. It is only the last outermost layer of a nested motion so deep and so old that peeling it apart takes a documentary, not a paragraph. Beneath it lies your spin around Earth's axis, and Earth's fall around the Sun, and the Sun's long slow drift around a spiral arm, and the spiral arm's drift around a galactic core, and the galaxies plunge toward a companion, and the companions plunge toward something enormous and half-hidden, behind the dust of our own sky, something we can barely see and cannot quite name. You're not sitting still. You have never sat still. Nothing you have ever done in your entire life has been done while at rest, and yet the chair is steady. The lamp does not swing, the floor does not tilt. Your inner ear, which is a small and honest instrument, reports nothing. This is the mystery this whole story is built around, and it is stranger than it first sounds, because the question is not simply how fast are you moving. The question underneath is whether that question even has an answer, whether the phrase not moving describes anything real, or whether it is only a statement about who is asking, whether the universe contains, somewhere in its architecture, a place a thing could genuinely be at rest, or whether stillness itself is a kind of illusion the mind produces to keep from falling over. Over the next hours we are going to walk that question out to its edge. We will follow it from a chair in a quiet room to the surface of a spinning planet, from a spinning planet to a star drifting through a galactic arm, from a galactic arm to a river of galaxies flowing towards something vast and unseen. We will meet the philosophers who insisted the Earth could not possibly move, and the astronomers who proved it did. We will meet the experiment that went looking for the wind of space and came back with nothing. We will meet the two men at a New Jersey telescope who found the faint hiss of the beginning of everything by accident, and thought at first it was the droppings of pigeons, and we will meet the number 370 kilometers per second, and we will name every motion it is hiding one layer at a time until you can feel the full shape of the address you are travelling through space at this moment. If this is the kind of thing that pulls you deeper the longer it goes, the kind of question you'd rather sit inside than solve quickly, then you're in the right place. Settle in. Dim the light a little further if you like. Let's begin. Start with the chair. Start with the room. Start with the astonishing fact that your body, evolved across billions of years on the surface of a moving world, has no organ dedicated to detecting that motion. You have organs for temperature. You have organs for pressure, for balance, for the direction of gravity, for the tilt of your head. You have receptors that can sense a single photon in a dark room, and hair cells that can register vibrations quieter than the noise of your own blood. But of the fact that the ground beneath you is spinning eastward at over 1,000 kilometers per hour, the fact that you and everyone you have ever loved have been hurled around a central axis every day of your lives, of that, nothing. No sensation, no warning light, no whisper. There is a reason for this, and the reason is the first crack in the comfortable lie. Your body cannot feel constant velocity because constant velocity feels exactly like rest. This is not a failure of biology. It is a property of the universe. A traveller in a smoothly moving train, curtains drawn, cannot tell whether the train is moving at 80 kilometers an hour or standing perfectly still at a platform. A passenger in an aeroplane cruising at 900 kilometers an hour can pour coffee into a cup, as if the aircraft were parked on a runway. Motion, when it does not change, hides itself. It leaves no trace on the senses, it leaves no trace on the physics, and this is not a quirk of trains or aircraft. It is a rule that runs all the way down to the deepest laws we know, which means that when you sit in your chair and feel absolutely at rest, you are receiving a report from a nervous system that is telling you, with complete honesty, only what it can measure. It cannot measure your motion around the Earth's axis because that motion is smooth. It cannot measure your motion around the sun because that motion is smooth. It cannot measure the sun's motion around the galaxy because that motion is smooth. Every layer of your travel is silent for the same reason a train ride is silent, because uniform motion has no fingerprint. What we call stillness is not the absence of motion. It is the absence of change in motion, and those are very, very different things. You can, if you want to, feel a hint of it. Stand outside on a clear night, away from streetlights, and look up. Watch the stars long enough and you will see them move. They rise in the east and set in the west and cross overhead in slow arcs, and the ancient intuition, the one that lived in the human eye for tens of thousands of years, was that the stars were doing the moving and the ground was standing still. It is a beautiful, sensible, entirely wrong idea. It is the ground that is moving. It is you that is turning. The stars are simply hanging there, indifferent, while your planet swings you past them at over 1,000 kilometers an hour. But nothing in your body knows this. Your body only knows that the chair is steady, and the lamp does not swing, and the floor does not tilt. Your body is telling you exactly the truth it is equipped to tell. It is the truth that is incomplete. And so we arrive at the central question, and it is worth stating it plainly, because the whole shape of what follows is set by it. Is there any frame of reference in which you, right now, sitting in your chair, are genuinely, absolutely not moving? Not appearing to be at rest, actually at rest in some deep sense, the way a philosopher would want the word to mean? Is there a place a thing could stand and be still against the whole universe, and know it? Or is stillness always relative, always a statement about who is asking, always dependent on where the observer happens to be sitting, always a comparison and never a fact? Rest with that for a moment, because the answer is going to take us places you might not expect. For most of human history, the answer seemed obvious. Of course there is such a frame. It is the earth. It is the ground beneath your feet. The world is the thing that does not move, and everything else, the sun, the moon, the stars, the wandering planets, turns around it. This was not a wild guess. It was the accumulated common sense of every civilization that had ever bothered to look up. You could feel it in your bones. Drop a stone, and it falls straight down. It does not curve away as it would if the ground were rushing sideways beneath it. Watch the horizon. It does not tilt. Listen for the wind of your motion. There is none. The earth was the unmoved centre, and every appearance confirmed it, and for nearly 2,000 years the greatest minds in the Western tradition built a physics, a cosmology, and eventually a theology on top of that single load-bearing assumption. The man whose thinking framed it most durably was Aristotle. In the 4th century before the Common Era, in the school he founded outside Athens, Aristotle worked out a picture of the cosmos so internally consistent, so aesthetically satisfying, so aligned with the visible evidence, that it would organize European thought for the next 1400 years. The universe, Aristotle argued, was a finite sphere. At its center sat the earth, heavy and cold and unmoving. Around the earth turned a nested series of transparent crystalline shells, each carrying one of the wandering lights of the sky, the moon on the nearest sphere, then Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the outermost sphere of the fixed stars, all of them turning around us in serene, unhurried, eternal circles. The shells were not empty. They were made of a fifth substance, quintessence, or ether, a perfect, incorruptible material unlike anything in our lower world. Down here, in the sublunary realm beneath the moon's orbit, things were mixed and messy. Earth, water, air, and fire, forever combining and separating, forever changing, forever dying. Up there, above the moon, nothing changed. The heavens were perfect, the circles were perfect, the motion was perfect, and the earth, at the bottom of it all, was not merely still by accident, it was still by nature. The heavy elements had, in Aristotle's physics, a natural tendency to seek the centre of the universe, and since Earth was made of the heaviest stuff, it had settled at that centre and could not go anywhere else. To move the Earth would require what Aristotle called a violent motion, a force acting against nature, and such a force at planetary scale was unthinkable. This is important, because it shows you how deep the assumption ran. The Earth was not just observably at the centre, it had to be. It could not be otherwise without breaking the whole logic of how heavy things behaved. Rest, at the centre, was Earth's natural state. Anywhere else was philosophically impossible. 5 centuries later, in the great multicultural city of Alexandria, an astronomer named Claudius Ptolemy took Aristotle's picture and made it work. Not just philosophically, mathematically. Because there was a problem. The planets, if you actually watched them carefully, did not move in the serene circles the theory required. Mars, in particular, misbehaved. Every so often it would slow, stop against the background of the stars, reverse direction for weeks, stop again, and then resume its ordinary motion. This is what astronomers call retrograde motion, and to a system built on perfect uniform circles it was an embarrassment. Ptolemy's solution, laid out in a 13-book treatise around the middle of the 2nd century of the Common Era, a work later known by the Arabic name the Almagest, meaning simply the greatest, was to add wheels to the wheels. A planet did not move in a single circle around the Earth. It moved in a small circle, and the centre of that small circle moved in a larger circle. The small ones he called epicycles, the larger ones he called deferents, and by adjusting the sizes and the speeds of these nested circles, one could reproduce with astonishing accuracy the observed positions of the wandering stars. When even that was not enough, Ptolemy introduced another device, a point offset from the true centre called the equant, from which a planet's motion appeared uniform even though it was not. The system grew intricate, it grew baroque, but it worked. It predicted where the planets would be tomorrow, and next year, and a century from now, and it did so well enough that for nearly 1400 years no one had a better tool. The Almagest also contained something else, a catalogue of over 1,000 stars, arranged into 48 constellations, with coordinates careful enough to be usable for navigation and for cartography, deep into the modern era. It was, in every sense, the reference book. When the Roman Empire dimmed in the west, the book travelled east. Scholars in Baghdad and Damascus and Cordoba read it, copied it, corrected it, extended it. In the 12th century it came back to Latin Europe through the translation work of Gerard of Cremona, and it settled into the scholastic curriculum as the foundation of astronomical study. To question the Almagest was to question the intellectual architecture of the medieval world. And here we should pause because it is easy from our vantage to smile at all this. Crystalline spheres, epicycles, an Earth that could not move because it had settled at the bottom of things. It sounds like the picture of a childlike cosmos, waiting to be corrected. But it was not childlike, it was rigorous, it was mathematical. It answered its own strongest objections. Ptolemy himself considered the possibility that the Earth might rotate on its axis, and rejected it not out of dogma but out of physics. If the Earth was spinning, he reasoned, then a stone dropped from a tower would land far to the west of where it was released, and birds would be flung off into the sky, and clouds would stream across the heavens in a permanent wind. None of this happened. The reasoning was wrong, but only because it rested on a theory of motion that would not be corrected until Galileo. Given the physics available to him, Ptolemy was being careful, not foolish. And then there was parallax. If the Earth moved around the Sun, Ptolemy argued, then the nearer stars ought to shift over the course of a year against the more distant ones, the way a nearby lamppost shifts against the far mountains when you sway from side to side. No such shift could be seen. The stars stayed exactly where they always were. From this, Ptolemy drew a correct inference and a mistaken conclusion. The correct inference was that if the Earth did move, then the stars must be at astonishing distances, so far away that the annual sway of an orbit would be too small to detect. The mistaken conclusion was that this was so unlikely as to be dismissed, and so the Earth was still, and the sphere of the stars turned above it, and everything held together. For 1400 years, this was the picture. Not a picture that survived by inertia alone, a picture that predicted eclipses and equinoxes and the risings of planets, that fitted the visible sky, that harmonized with the physics of falling stones, that spoke to the philosophical intuition that heavy things fall to a center, and that Earth, being heaviest, must sit there. It was, in its way, one of the most successful ideas the human species has ever produced. And the fact that it was wrong is a strange thing, because being wrong was not enough to unseat it. What was needed was someone willing to move the Earth on purpose, and to work out what the sky would look like if you did. That someone was a Polish canon named Nicholas Copernicus. He was born in 1473 in a merchant town along the Vistula, into a Europe where the Almagest still ruled and the crystalline spheres still turned. He studied law. He studied medicine. He worked as an administrator for the cathedral at Frombork, a small town on the Baltic coast where the wind came in cold off the sea, and the tower of the cathedral offered a good view of the night sky. And somewhere in the quiet of that life, he began to entertain a suspicion. The suspicion was not that Ptolemy's numbers were wrong. The numbers were actually quite good. The suspicion was that the system that produced them had become ugly. Wheels upon wheels, offsets upon offsets, the equant fudging the uniformity of motion to preserve the appearance of uniform motion. Copernicus found it inelegant. He thought a simpler picture might be possible. What if the sun, not the Earth, sat at the centre? What if the Earth was simply another planet turning on its axis once a day and circling the sun once a year? Retrograde motion would no longer require epicycles. It would be a natural consequence of the Earth overtaking a slower outer planet, the way a faster car appears to slide backward past a slower one on a parallel road. The whole system would become simpler. It would become, in a word he might have used himself, more beautiful. He worked on the idea for decades. By 1514, he had circulated a short, untitled manuscript to a handful of trusted friends, an outline of the new system, which later scholars would come to call the Commentary Olus. He kept refining it. He kept computing. He was, by temperament, cautious, a man who understood exactly how disruptive his book would be if he ever finished it, and so he did not finish it in a hurry. The manuscript grew across the years between 1520 and 1541, and it might have grown longer still had a young mathematician named Georg Joachim Rheticus not arrived at Frombork in 1539 and, over the following months, coaxed the older man toward publication. In 1540, Rheticus published a preview of Copernicus's ideas, the Narratio Prima, a first account of the new system to test the reaction of European scholars. The reaction was survivable, and so, at last, the book was sent to a printer in Nuremberg. It was called De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, and it was published in 1543, dedicated to Pope Paul III by the printer Johannes Petreius. The story that has come down to us is that a first printed copy was placed in Copernicus's hands as he lay on his deathbed. Whether he was conscious enough to understand what he held, we do not know. He died that year, and the book began its slow, quiet work. Slow, because the reception was not what one might expect. There was no immediate storm. Part of this was accidental. The man who oversaw the printing, a theologian named Andreas Osiander, had inserted an anonymous preface, without Copernicus's approval, that presented the heliocentric model not as a claim about the physical world, but as a mathematical hypothesis, a convenient device for computing planetary positions. Take it as a tool, the preface suggested, not as a truth. For a generation, this framing helped the book pass through the world without attracting the storm that would eventually gather around it. Astronomers used the tables, they admired the elegance. They did not mostly feel their souls to be in danger, but an idea like this does not stay a convenience. If the Earth truly moves, if it is not the still centre of the world but one of several bodies rolling around a common fire, then Aristotle's physics is broken, and the crystalline spheres are broken, and the natural place of heavy things is broken, and the theology that had wrapped itself around 14 centuries of geocentric certainty begins to feel a wind under its floorboards. The book was a slow fuse. It would take another lifetime for the burn to reach the powder. That lifetime belonged to Galileo Galilei. He was born in Pisa in 1564, 21 years after Copernicus's death, and he lived until 1642, dying at Arcetri near Florence in an old age of quiet house arrest. In between, he did something Copernicus had never been able to do. He looked. The instrument was new. A Dutch spectacle maker had, a year or two earlier, arranged 2 lenses in a tube in such a way that distant things appeared close. Galileo heard rumours of the device in 1609 and, without ever seeing one, worked out the geometry himself and built better ones. By the end of that year he had a telescope that magnified about 20 times, a small brass and leather tube that could reveal features of the sky no eye had ever seen before. And on the 7th of January 1610, in the late evening, he turned it toward the largest of the wandering planets, toward Jupiter, hanging bright above the Italian horizon, and he saw something he did not expect. Beside the planet, strung out in a neat line, were 3 small bright points. He thought at first that they were faint background stars that happened to lie along Jupiter's path. But the next evening he looked again, and the little stars had moved, and they had moved the wrong way, in the wrong direction for background stars carried by the turning of the sky. That caught his attention, He watched again on the 11th, and there were 2. On the 12th, 3 again. On the 13th, 4. 3 on one side of the planet and 1 on the other. By the 15th of January he had understood what he was seeing. These were not stars, they were moons, 4 small bodies orbiting Jupiter, tracing their own small circles around a body that was not the Earth. Think, for a moment, about what that meant. In the Ptolemaic universe, every celestial body turned around the Earth. That was the rule, that was the architecture. But here, plainly, in a telescope any competent instrument maker could reproduce, were 4 bodies turning around something else. The rule had an exception, and if there was one exception, the rule was no longer a rule. Galileo published his observations in March of 1610 in a slim, urgent little book called Siderius Nuncius, the Starry Messenger. He named the 4 moons the Medicean stars, in a canny bid for patronage, and it worked. Cosimo II de' Medici invited him to Florence as court philosopher and mathematician. The names did not last. The moons we now call Io, Europa, Ganymede, and Callisto, the Galilean moons. But the discovery did, and there was more. In October of that same year, Galileo turned his telescope toward Venus, and over the following months he watched the planet do something the Ptolemaic system said it could not do. It went through phases. It began as a thin crescent, waxed slowly toward a fuller disk, and waned again to a crescent exactly like the moon. In Ptolemy's arrangement, with Venus riding on an epicycle between the Earth and the Sun, this sequence of phases was impossible. A full disk of Venus could only be seen if the planet were sometimes on the far side of the Sun from us, which meant it had to be orbiting the Sun, not the Earth. Galileo held the observations back until his letter on sunspots in 1613, but the meaning was clear. The Ptolemaic system was finished. Venus had betrayed it. The Earth, it turned out, was a planet. It moved. It turned on its axis. It circled the Sun. The unmoved centre was not unmoved after all, and it was not the centre. The chair you were sitting in, the chair Aristotle had sat in, the chair Ptolemy had sat in, the chair every medieval scholar had sat in, believing themselves to be at the still hub of a turning cosmos. That chair had been moving the whole time. Nobody had felt it. Nobody could feel it. But the sky, once you looked at it through the right instrument, told you plainly. This was the first dislocation, the first great removal of the human observer from the privileged place of rest. It would not be the last. It would not, in fact, be anywhere near the last. Because once you accept that the Earth moves, the next question is inescapable. Moves with respect to what? Around the Sun, yes. But does the Sun itself stand still? And if the Sun does not stand still, then what does? Is there anything, anywhere, that a physicist could point to and say, there, that is the place where motion begins from, that is the frame against which all other motion is measured, that is the still point around which the turning world turns? The answer to that question would take another 300 years, and it would pass through a bucket of water on the floor of Isaac Newton's study, and a strange negative experiment in a basement in Cleveland, and the mind of a patent clerk in Bern who was, at the time, unemployable as a physicist. And it would leave us, at the end, with something none of them expected, a frame of reference woven into the sky itself, discovered by 2 engineers who thought at first they were listening to the noise of pigeons. Begin, then, with the bucket. It is a small object, an ordinary object, the kind of thing you might find in any English garden of the late 17th century, a wooden pail, a length of rope, a quantity of water, nothing in it that a farmer would not recognise, nothing that would draw a second glance from a servant crossing a courtyard. And yet, in the pages of the book that Isaac Newton finally allowed the world to see in 1687, the Philosophia Naturalis Principia Mathematica, the mathematical principles of natural philosophy, this bucket becomes something else. It becomes an instrument. It becomes an argument. It becomes, in a strange and quiet way, the last defence of a universe with a still point at its heart. Picture the scene as Newton describes it, because he wants you to picture it. He wants you to perform the experiment in the theatre of your own head. Take the bucket, tie the rope to its handle, suspend it from a beam so it hangs freely in the air. Now twist the rope, patiently, turn after turn, until it is coiled tight upon itself. Fill the bucket with water, not to the brim but nearly. Let the water settle. Let its surface become flat, flat as a table, flat as the still water in a well at dawn. And now, when everything's quiet, release the bucket. The rope begins to unwind, the bucket begins to turn. slowly at first, then faster. And here is the thing to watch, the thing Newton wants you to watch, the water inside. In the first instant, the water does not turn with the bucket. The bucket is spinning around it. The wood is rotating against the fluid, and the fluid is, for the moment, indifferent. Its surface remains flat. There is enormous relative motion between the bucket and the water, and yet the water, in itself, is calm. Then friction begins to do its work. The wooden walls drag the water into motion. Layer by layer, ring by ring, the water begins to spin. And as it spins, its surface changes shape. The centre dips, the edges rise. What was flat becomes a shallow bowl, then a deeper bowl, a curve that Newton and every mathematician after him would call a paraboloid. The exact geometry a rotating fluid takes when it settles into its motion. Eventually the water is spinning at the same rate as the bucket. There is no longer any relative motion between the two. The water is at rest with respect to the wood that contains it, and yet its surface is not flat. Its surface is deeply, unmistakably curved. Stop and feel the weight of that, because the whole logic of the experiment lives in this one small oddity. At the beginning, when the bucket was spinning and the water was still, there was tremendous relative motion, and the water's surface was flat. At the end, when the bucket and the water were spinning together, there was no relative motion at all, and the water's surface was curved. Whatever is causing that curve, whatever is pushing the water up the walls and hollowing the centre, it cannot be the motion of the water relative to the bucket. The relative motion, when the curve is at its deepest, is precisely zero, so the water is moving. But moving with respect to what? Newton's answer is one of the most audacious sentences in the history of physics. The water, he says, is moving with respect to absolute space, not the bucket, not the room, not the earth, not the stars, space itself, an invisible, unchanging, immovable backdrop against which all true motion is measured. He puts it in a phrase that would haunt physicists for the next 2 centuries. Absolute space, he writes, of its own nature, without reference to anything external, always remains similar and unmovable. Read that again, slowly. Without reference to anything external. Space, in Newton's picture, does not need matter to define it. It does not need a coordinate system laid down by observers. It does not need stars or planets or the walls of any bucket. It simply is. It is the stage, and every object in the universe, whether it knows it or not, is moving or standing still with respect to that stage, and the stage keeps a perfect, silent record of the difference. This is the ghost. This is the great ancient ghost that will walk through physics for the next 228 years, and it will take Einstein and general relativity and a change in the very meaning of the word geometry to lay it to rest. It is worth pausing on why Newton needed the ghost at all. He was not a mystical man in his physics, whatever else he may have been in his private notebooks. He was a mathematician of ferocious clarity. If he says absolute space exists, it is because he cannot make his mechanics work without it. And the reason is inertia. Inertia is the tendency of a body to keep doing what it is doing, to stay at rest if it is at rest, to keep moving in a straight line if it is moving. Newton's laws depend on inertia the way a house depends on its foundation. And inertia, Newton realized, requires a frame. If a stone resists being pushed, it is resisting acceleration. But acceleration with respect to what? Not with respect to any nearby object. Move the object and the stone still resists. The stone seems to know, all by itself, whether it is being accelerated or not. It seems to consult some external reference, some background against which its motion is judged. Newton looked at the bucket, looked at the curved water, and concluded that this reference must be real. The water knew it was spinning. It had to know it against something, and the only something large enough, silent enough, universal enough to serve was space itself. So the ghost was not a decoration on Newton's system. It was a load-bearing wall. Take it away, and the whole architecture of classical mechanics wobbles. Take it away, and inertia becomes mysterious. Take it away, and there is no such thing as true motion, only apparent motion, only the endless relative dance of one object with respect to another, with no umpire anywhere in the universe to say which of them, in the end, is actually still. For nearly 2 centuries, physicists lived comfortably with the ghost. They did not need to see it. They did not need to touch it. They only needed it to exist silently in the background of their equations, and everything worked. Planets orbited, cannonballs arced, tides rose. The Industrial Revolution was built in a very real sense on Newton's absolute space, because every calculation of every steam engine's piston relied on the mechanics that space made consistent. But a ghost, however useful, is still a ghost. And every so often someone would step forward and ask the awkward question. If absolute space is real, they would say, then surely we ought to be able to detect our motion through it. Surely there must be some experiment, some clever arrangement of mirrors or pendulums or clocks that would let us measure the Earth's true velocity, not with respect to the sun, not with respect to the fixed stars, but with respect to that silent, immovable stage, and every so often someone would try. The most sustained challenge came late, and it came from a physicist and philosopher named Ernst Mach, born in 1838, working across the second half of the 19th century. In his book on the science of mechanics, published in 1883, Mach did something quietly radical. He looked again at Newton's bucket and he said, "Perhaps the curve of the water is not evidence of absolute space at all. Perhaps it is evidence of the stars. Consider," Mach said, "when the water spins, its surface curves. Newton says, it curves because it is rotating with respect to absolute space. But there is another possibility. The water is also rotating with respect to every distant galaxy, every fixed star, every distant mass in the universe. What if it is that distribution of matter, the whole silent congregation of everything far away, that provides the reference frame? What if inertia is not a property that objects have on their own, consulting some empty backdrop, but a property that arises from the presence of all the other matter in the universe? What if the water knows it is spinning because the stars, in a sense, are watching? This idea, Mach's principle as it came to be called, was a profound and disturbing suggestion. It said that the local behavior of a small object depends on the global distribution of all matter, everywhere. It said that if you could magically remove all the distant stars, the bucket experiment would fail. The water would not curve, because there would be nothing left in the universe for it to rotate with respect to. Newton had made inertia local and absolute. Mach made it global and relational, and though Mach could not, in his own century, prove his idea, he planted a seed. That seed would grow, half a century later, into the young Einstein's imagination, and it would help pull physics away from the ghost. But we're getting ahead of ourselves. Come back to the bucket for one more moment. Come back to Newton in his rooms at Cambridge, in his small square garden, in the long candlelit evenings of the 1680s. The Principia is being written. Edmund Halley is coming and going, coaxing the manuscript out of him page by page, paying for the printing out of his own pocket because the Royal Society has spent its budget on a book about fish. Around Newton, the mathematics of the heavens is being assembled. The inverse square law of gravity, the three laws of motion, the calculation of the orbits, the tides, the shape of the Earth, and underneath it all, quiet, unobtrusive, indispensable, the scholium on absolute space, the stage on which all this mechanics performs, the frame against which the water in the bucket knows it is turning. Newton, one suspects, knew perfectly well that he could not prove absolute space existed. He could only argue that his mechanics needed it. That is not proof, it is inference, and it is honest. He says as much in his careful prose. True motion, he writes, is difficult to distinguish from apparent motion because the parts of absolute space cannot be seen. But this difficulty of seeing something, he insists, is not the same as the thing not being there. The bucket shows us that some motions are true and some are only apparent, and the difference is real, even if the backdrop against which it is measured is invisible. For 200 years that argument stood. It was not attacked because it did not need to be attacked. It worked. And when, in the 19th century, physicists finally did devise a way to try to see absolute space, to detect the Earth's motion through the silent stage, they thought they were about to give Newton one final glorious confirmation. They were about to do the opposite. The instrument that would try was the instrument nobody had yet imagined in Newton's time, because the medium it depended on had not yet been named. That medium was the luminiferous ether, the invisible substance that 19th century physicists believed must fill all of space in order for light to travel through it. Light, they knew, was a wave. Waves, they knew, needed something to wave in. Water waves need water. Sound waves need air. Light waves, therefore, must need something too. That something they called the ether, and they gave it whatever properties it needed to do the job. Perfectly transparent, perfectly frictionless, perfectly rigid to fast oscillations, perfectly yielding to slow-moving planets. It was in essence a 19th century form of the same ghost. It was Newton's absolute space with a chemical name, and crucially it was supposed to be detectable. If light travels at a fixed speed through the ether, and if the Earth is moving through the ether, then the speed of light measured on the moving Earth should depend on the direction you measure it. Light travelling in the direction of the Earth's motion should appear to go a little slower than light travelling across it, just as a swimmer moving upstream in a river makes less headway than one crossing it. Measure the difference, and you measure the Earth's velocity through the ether. Measure that, and you measure the Earth's velocity through the last, best candidate for Newton's absolute frame. That is the experiment that Albert Michelson set out to perform. He was born in 1852 in a small town in what is now Poland. His family emigrated to America when he was a boy. He rose through the United States Naval Academy, through European laboratories, through a growing reputation as the most delicate measurer of light the world had. He was patient in a way that suggests something almost monastic, a man for whom a fringe shift of a fraction of a wavelength was worth months of preparation. In the mid-1880s, he took up a post at the Case School of Applied Science in Cleveland, Ohio, and he found there a collaborator, Edward Morley, a chemist across the street at Western Reserve University, who shared his temperament and his obsession with precision. Together, in the spring and early summer of 1887, they built one of the most exquisite instruments in the history of 19th century physics. It was an interferometer, a device that splits a beam of light into two, sends the two halves along perpendicular paths, bounces them off mirrors, brings them back together, and lets them interfere. If the two paths take exactly the same amount of time, the recombined light shows a particular pattern of bright and dark fringes. If one path takes very slightly longer than the other, even by a small fraction of a wavelength, the fringes shift. And the beauty of it is this: rotate the whole apparatus so that the arm which pointed along the Earth's motion now points across it, and the fringes should shift again in a predictable way by an amount that measures the ether wind. The engineering demanded of them was almost cruel. The whole instrument had to sit on something so stable that the trembling of a carriage rolling by outside would not spoil the measurement. Their solution was a slab of sandstone, a great block of stone, roughly square, thick and heavy, floated on a shallow trough of liquid mercury so that the entire apparatus could be turned smoothly, silently, without the tiniest jolt from a bearing or a rail. Push it, and it would revolve slowly, silently, on its bright metallic sea, for hours if you let it. The interferometer sat on top of this stone island, its arms crossing at right angles, mirrors and lamps and eyepieces arrayed around a central splitter. The whole assembly lived in the basement of a university building, insulated from the sun, from the temperature swings of the Ohio sky, from every source of vibration Michelson and Morley could think to muffle. They worked at night, they worked at dawn, they worked in short, careful sessions because a human being staring into an interferometer for too long begins to see fringes that are not there, and their prediction, when the paper was written, was quantitative and clean. If the Earth is moving through the ether at roughly the speed of its orbit around the Sun, about 30 kilometers per second, then rotating the apparatus should shift the fringes by around 4/10 of a fringe. Not a whole fringe, but enough. Enough to see, enough to measure, enough to publish and become famous by. Michelson had done a smaller version of this experiment years earlier in Germany, and had already seen a hint that the shift was too small. But that earlier attempt had been rough. Now, in Cleveland, with Morley's chemistry and their combined patience, and a slab of stone on a lake of mercury, the answer would be definitive. They ran the experiment, they rotated the stone, they watched the fringes. Nothing happened. Not quite nothing. There is always noise, always the small drift of temperature and the small tremor of the mercury and the small human error of the observer at the eyepiece. But nothing that could plausibly be called a shift. Nothing that could plausibly be called the 4/10 of a fringe their theory demanded. The fringes sat stubbornly where they were. The Earth was moving. The ether, if it was there, should have been streaming past them. And yet, wherever they pointed the arms of their instrument, light behaved as if there were no wind at all. They rotated the stone again. They came back the next night, and the next, and the night after that. They ran the experiment through different hours to catch the Earth at different angles in its orbit. They ran it in April. They ran it in July. They looked for the signal at every hour of the day. And through all of it, the fringes stayed where they were. They published the result in the American Journal of Science in November of 1887. in the careful, measured prose that scientific journals demanded. It appears, they wrote, reasonably certain that if there be any relative motion between the Earth and the luminiferous ether, it must be small. Small enough, they went on, to entirely refute the standard explanation of how starlight is bent by the Earth's motion. The wording is polite, the implication is a bomb. Because the null result of Michelson and Morley was not simply the failure of one experiment, it was the failure of the whole 19th century picture. Either the Earth was not moving, which was absurd because the Earth was demonstrably in orbit around the Sun, or the ether was moving with the Earth, dragged along like a cloak which contradicted the way the ether was supposed to work, or the ether did not exist. And if the ether did not exist, then the last physical candidate for Newton's absolute space, the last invisible medium that might have carried the ghost of the immovable backdrop, had vanished. There was nothing left to detect, there was no wind, there was no stage. You have to understand what this did to physicists. It did not, at first, look like a revolution. It looked like a puzzle. It looked like an experimental failure that would surely, with more work, be tidied away. Someone would find a subtle error. Someone would propose a modification of the ether. Perhaps it was partly dragged. Perhaps objects moving through it were slightly squeezed. Perhaps clocks moving through it ran slightly slow. That would rescue the picture and preserve the ghost. Several such modifications were in fact proposed. The Irish physicist George Fitzgerald and the Dutch physicist Hendrik Lorentz offered contraction hypotheses so ingenious that they very nearly worked. But every rescue involved introducing effects, length contractions, time dilations, that were themselves so strange that they raised more questions than they answered. Physics did not so much solve the problem as build scaffolding around it and hope, quietly, that someone would arrive with a hammer. For 18 years that scaffolding stood. From the publication of Michelson and Morley's paper in 1887, through the last years of the 19th century, through the first years of the 20th, the ether hung on by its fingernails. Textbooks still described it. Lectures still invoked it. Instruments were still designed on the assumption that it must be there, hiding, if only they could catch it. The community of physicists knew, in the way a family knows about a serious illness, that something was wrong. They did not yet know how wrong, or how deep the wrongness went. The man who would tell them was, in 1887, an 8-year-old boy in Munich. He was slow to speak. His teachers found him withdrawn, sometimes sullen, unimpressed by the drills of the classroom. His father ran a small electrical business that was, at the time, not doing especially well. Nothing about him would have struck a visitor as remarkable. He liked music. He liked geometry. He liked, when nobody was watching, to sit quite still and think about very simple things until they became very strange. His name was Albert Einstein, and by the time he was 26, working, of all things, as a junior clerk in the patent office in Bern, examining applications for electrical devices in a small crowded room, he would have written the paper that made the ghost, at last, walk out of physics. But that is a story for a little later. First, we must sit with the crisis a moment longer, because it is important to feel, before the resolution comes, how truly stuck physics was. The whole edifice built by Newton, the beautiful, exact, universally trusted edifice of mechanics, rested on a backdrop that could not be seen. For 2 centuries that had been fine. Now, at the end of the 19th century, an experiment of extraordinary precision had gone looking for the last physical trace of that backdrop, and had come back with empty hands. The stage, if it existed, was undetectable. The wind, if it blew, blew without any effect. The ghost, if it walked, walked without leaving footprints. And in the silence of that null result, in the strange stillness of the fringes that would not shift, a very old question began to reopen. Not this time the medieval question of whether the earth was at rest. That question Galileo had answered. The new question was subtler, and it went beneath Copernicus, beneath Galileo, beneath Newton himself. If there is no ether, and if there is no absolute space, then the whole notion of true motion, the distinction Newton had drawn between motion that is real and motion that is only apparent, begins to dissolve. There is only motion with respect to something else. There is only relation, and the still point of the turning world, the frame against which all velocity is measured, is nowhere to be found. The bucket still curved. Somewhere in Cleveland, a slab of sandstone still floated silently on its Mercury lake, and in a patent office in Bern, a young man had just begun, in the margins of his working days, to imagine what it would mean if the speed of light were the same for every observer, no matter how fast they were moving. He arrived at the patent office in the summer of 1902. Bern was, at that time, a quiet capital. Sandstone arcades, a river the colour of glacial silt looping around the old town, a clock tower whose mechanism had been keeping the city's time for centuries. The Federal Office for Intellectual Property stood at the corner of Speichergasse and Genfergasse, a plain building among plainer ones, and inside it a young man with unruly hair and a poorly knotted tie sat down at a wooden desk to examine drawings of switches, dynamos, and the small ingenious devices by which the electrified world was reshaping itself. He was 23. He had failed to secure an academic post. He had taken this job because a friend's father had helped him get it. He was, on paper, a technical expert of the third class, probationary, salary 3,500 Swiss francs per year. Enough to marry on, enough to eat on, not enough to be comfortable. He would later call this office his worldly cloister, the place, he said, where he had hatched his most beautiful ideas. It is worth pausing on that phrase. A cloister is not a laboratory. A cloister is a place where the outer world is held at a certain distance so that an inner world can breathe. The patent office was not glamorous, it was not prestigious, but it had two qualities that a young theoretical physicist could not have found in a lecture hall. It gave him a steady wage so that he did not have to please anybody in order to eat, and it gave him, once his day's work was efficiently dispatched, a certain quantity of quiet in which to think. He thought about very simple things. He thought about what it would mean to ride alongside a beam of light. He thought about what a clock on a moving train would show to a person standing on the platform, and what the same clock would show to a person sitting inside the train, and whether those two people could ever agree. He thought about magnets and coils and the smaller symmetries that had crept into the theory of electricity, asymmetries that seemed to depend on which of two identical objects you decided was moving. These questions did not require expensive equipment. They required a piece of paper, a pencil, and the patience to hold a very simple picture in the mind until it began, quietly, to come apart. By the spring of 1905, something was gathering. He wrote to his friend Conrad Habicht, a young man with whom, along with Maurice Solovine, he had formed a small, half-joking reading club they called the Olympia Academy, and promised him 4 papers, each, he suggested with dry amusement, revolutionary in its own small way. He was not exaggerating. Between March and September of that year, in the small hours snatched from a patent examiner's schedule, he sent 4 papers to the German journal Annalen Physik. One explained the photoelectric effect by treating light as though it came in discrete packets, a paper for which, 16 years later, he would receive the Nobel Prize. One accounted for the jittery motion of pollen grains suspended in water, and in doing so gave physics one of its cleanest arguments for the reality of atoms. One was a short, almost casual note showing that mass and energy were, at some deep level, the same thing, and one, submitted on the last day of June and published on the 26th of September, was titled, with the flat descriptive modesty of the era, on the electrodynamics of moving bodies. That paper did not, at first glance, announce itself as a hammer. It began politely, almost apologetically, by pointing out a small awkwardness in the way physics described a magnet and a coil of wire moving relative to one another. Depending on which one you called stationary, the equations gave the same answer by 2 entirely different routes. This asymmetry, Einstein observed, did not seem to belong to nature. It seemed to belong to the way we had chosen to describe nature. And from that quiet dissatisfaction, he built the rest. He asked his reader to accept 2 principles. The first was that the laws of physics take the same form in every inertial frame of reference. There is no experiment you can do inside a smoothly moving laboratory that will tell you how fast the laboratory is going. The second was that the speed of light in empty space has one and the same value for every observer, regardless of how the source of the light is moving and regardless of how the observer is moving. Not almost the same value, not the same value up to a small correction, exactly the same value. Always. Sit with that for a moment. The first principle is old. It goes back in a certain form to Galileo, who had noticed that a passenger below decks on a smoothly sailing ship cannot, by any local experiment, distinguish the moving ship from a ship at rest in the harbour. The second principle is where the hammer falls, because if you and I are moving toward one another, and I flash a beam of light in your direction, ordinary common sense insists that you should measure that light as arriving a little faster than I do, by exactly the amount of our approach. Every intuition we possess about how speeds add up demands this. And Einstein's second postulate says, no, you measure the same speed I do, down to the last decimal, down to the last significant figure your instruments will allow. Everything else in the paper, every strange consequence, every apparent paradox, every reshaping of the fabric of common sense, falls out of holding those two statements together and refusing to let either of them go. Time, it turned out, could no longer be one single river flowing at one single rate for all observers. Two clocks moving relative to one another would not in general tick at the same rate. Two events that one observer called simultaneous would, to another observer moving at a different velocity, occur at different moments. Length itself was no longer absolute. A rod carried past you at high speed would measure, in your frame, a little shorter than the same rod at rest beside you. Mass, energy, momentum, all had to be rewritten. The rescue that Lorentz and Fitzgerald had proposed as a strange patch on a broken theory, the contractions, the local time, turned out in Einstein's hands to be no patch at all. They were the honest description of a universe in which the speed of light was a genuine constant. And in the middle of all this, quietly, without fanfare, the ghost walked out. There is no need, Einstein wrote, in more or less those terms, for the notion of a luminiferous ether. There is no need for the notion of an absolute space sitting behind the world, providing the true frame against which all velocities are secretly measured. Newton's backdrop, invisible and undetectable, that Michelson and Morley had spent a year of their lives trying to catch a breath of wind from, Einstein simply set it down. He did not disprove it in the ordinary sense. He showed that physics did not need it. And once physics did not need it, there was no experiment that could ever bring it back. Think about what that meant for the question we started with. For 2 centuries, an educated person could still ask in principle whether they were truly at rest or truly moving. There was a right answer, even if nobody knew how to find it. After 1905, the question itself began to fall apart. There is no such thing as being truly at rest. There is no such thing as being truly in motion. There is only being at rest or in motion with respect to some other thing. The chair you feel supporting you is at rest with respect to the floor. The floor is at rest with respect to the building. The building is at rest with respect to the ground. And the ground, along with the building and the chair and you, is turning and orbiting and drifting and falling, all at once, with respect to every other thing in the sky. None of those motions is more real than any other. Each of them is a relationship. And the whole idea of a still point at the centre of the turning world, the idea Aristotle had placed at the earth, that Ptolemy had elaborated with epicycles, that Copernicus had shifted to the sun, that Newton had abstracted into absolute space, that idea at last dissolved. The paper was published, and almost nothing happened. There was no press release, there was no thunderclap. Annalen der Physik was a respected journal, but it was a journal for professionals, and the paper was one of many. The young patent examiner went back to his desk on the Monday and continued examining applications for electrical apparatus. His salary did not change. His title did not change. It would take years for the paper's implications to filter through the community. A few of the great figures of the day, Max Planck among them, read it, and slowly began to understand that something extraordinary had happened. But for most of the physics world, in most of the year 1905, the ghost's departure went unremarked. Einstein was promoted at the office in the spring of 1906 from technical expert 3rd class to technical expert 2nd class, with a modest raise. He continued to think, at his wooden desk, in the small hours, about very simple things. Let that settle a moment. The most consequential shift in our picture of motion since Copernicus was written by a 26-year-old civil servant in his spare time in a small office in Bern and delivered to the world in the pages of a technical journal, and for a while almost nobody noticed. Physics does not always announce its turning points with trumpets. Sometimes they arrive in the mail, but the consequences, once they began to move, moved with a certain terrible thoroughness. Newton's laws, it turned out, were not wrong in the domain where we live. They were an extraordinarily good approximation, accurate enough to send probes to the outer planets, accurate enough to describe the tides and the seasons and the fall of an apple. Where they broke down was at very high speeds and in very precise measurements of small effects. There was, for instance, a small anomaly in the orbit of Mercury, a shift in the point of closest approach to the Sun that Newtonian gravity could not quite explain, amounting to about 43 arc seconds per century, a fraction so tiny that a lesser theory might have shrugged and blamed observational error. Einstein, 10 years later, in his general theory of relativity, would explain it exactly. Newton had been right about almost everything. Just, in the end, not everything. Now, having dispatched the ether and the absolute frame, having, one imagines, dusted his hands and returned to his patent applications, Einstein might reasonably have expected the question of a universal standard of rest to be closed. It was not. In fact, from the moment his paper was published, the universe was already preparing to raise the question again, in a form nobody had anticipated, from a direction nobody had thought to look. Consider what physicists in the first decades of the 20th century believed about the larger scales of the world. They believed that the Milky Way was essentially the universe. The faint smudges visible in telescopes catalogued for centuries as nebulae were assumed by most to be clouds of gas within our own galaxy. The universe as a whole was thought to be static, not expanding, not contracting, not doing anything on the larger scales but sitting there, eternal and unchanging, an infinite room full of stars. When Einstein extended his theory of relativity to gravity and to the universe as a whole, in 1915 and again in 1917, he found, to his considerable discomfort, that his equations did not want to give him a static universe. They wanted the universe to be doing something, expanding or contracting or oscillating. To hold it still, he inserted into his equations an extra term, a constant, which he would later regard with some regret. He wanted the universe to sit quietly. His mathematics wanted the universe to move. In Belgium, a young priest and physicist named Georges Lemaitre was reading those equations without Einstein's preference for stillness. Lemaitre had been born in 1894, had served in the Belgian army during the First World War, and had returned to study both theology and mathematics. He was ordained in 1923. And in 1927, working at the Catholic University of Leuven, he published a paper, in French, in an obscure journal, the Annales de la Société Scientifique de Bruxelles, under the modest title A Homogeneous Universe of Constant Mass and Increasing Radius, accounting for the radial velocity of extragalactic nebulae. In it he derived, from Einstein's own equations, a universe that was expanding, and he derived a relationship between the distance of a faraway object and the speed at which it appeared to be receding from us. The farther, the faster, in direct proportion. Lemaitre's paper was at first almost entirely ignored. It was published in a Belgian journal in French. Einstein, when Lemaitre visited him and explained the work, is reported to have said, in more or less these words, that the mathematics was correct but the physics was abominable. The universe, he still felt, ought to sit still, and so the paper sat too quietly on a shelf waiting for the world to catch up. Meanwhile, in California, on a mountaintop above Pasadena, another man was pointing an enormous new telescope at those very same nebulae. Edwin Hubble, tall, pipe-smoking, given to a slightly affected English manner, picked up during his time as a Rhodes Scholar, was working with the 100-inch Hooker telescope at Mount Wilson Observatory. It was, at the time, the largest telescope in the world. And on the nights of October 5th and 6th, 1923, Hubble had done something extraordinary. He had identified, in the great smudge of the Andromeda Nebula, a particular kind of star, a Cepheid variable, whose intrinsic brightness could be calculated from the rhythm of its pulsation. By comparing the intrinsic brightness to how bright it appeared, he could compute the distance, and the distance was staggering. Andromeda was not, as many had assumed, a cloud of gas inside our own galaxy. It was a galaxy in its own right, hundreds of thousands of light-years away, and the number would grow with better measurements. The universe was suddenly, catastrophically, larger than it had been the day before. Hubble kept working. He measured the distances to more and more of these extragalactic nebulae, and he began to combine his distances with measurements, made by others, of the speeds at which those objects were moving toward or away from us, speeds derived from the slight shifts in the colours of their light, the same Doppler effect that changes the pitch of a passing siren. And he began to see a pattern. The farther a galaxy, the faster it was receding. On the 15th of March 1929, in the Proceedings of the National Academy of Sciences, in a short paper called A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae, he published the result. The relationship was, within the scatter of his measurements, a straight line, distance and velocity marching in direct proportion, exactly what Lemaitre had derived 2 years earlier from Einstein's equations. The universe was running away from itself. In every direction we looked, the galaxies were flying apart, Not moving through space exactly, in the sense that a car moves through a landscape. The space itself was expanding, carrying the galaxies with it, stretching the light from distant objects toward the red end of the spectrum as it travelled. What Hubble had discovered, and what Lemaitre had predicted, was that the universe had a history. It was not eternal. It had been smaller once. It had been denser once. And if you ran the film backwards far enough, you arrived at something Lemaitre, drawing on his particular vocabulary, would later call the primeval atom, a moment when everything had been packed together into a state unlike anything we could easily picture, what we now call the Big Bang. Set aside for a moment the enormity of that historical claim. Return to the question we have been tracking all along. If everything is receding from everything else, if every galaxy is flying away from every other, then relative to what are all these galaxies moving? Once again, the question of a universal standard of rest peers up out of the ground where physics had thought it buried. Einstein had said, quite firmly, that no inertial frame is privileged. All are equally good for writing the laws of physics. And yet, on the larger scales, there was clearly some kind of average motion of matter, some frame in which, when you looked out in all directions, the universe looked roughly the same, the galaxies receding uniformly on every side. Any observer moving with respect to that frame would see the recession as slightly lopsided, a little faster in the direction of their motion, a little slower behind them. In principle, then, one could define a frame, not by fiat, not by philosophy, but by the actual arrangement of matter, in which the expansion looked most symmetric. A frame, one might carefully say, in which one was at rest with respect to the universe as a whole. That was not the ether. It did not violate relativity. It was not an invisible medium threading through space. It was rather a frame picked out by the universe itself, by the way its contents happened to be arranged and moving. Einstein's ghost had been laid to rest. But the universe apparently had a preferred frame of its own to offer, quite freely, once anyone thought to look. Nobody yet knew how to look. Lemaitre's expanding universe and Hubble's measurements gave the frame in principle. To find it in practice, to point at a particular direction in the sky and say, with an instrument, we are moving this fast, this way, with respect to the great whole, would require a signal nobody had yet imagined receiving. A signal older than the galaxies. A signal from the moment when the universe first became transparent to its own light. And it would come, when it came, not to an observatory on a mountaintop, and not to a purpose-built cosmological instrument, but to a large aluminum horn on a low hill in New Jersey, pointed at the sky by two young radio engineers who were trying, at first, only to get rid of a strange and persistent hiss. The hill was called Crawford Hill. It rose gently out of the flat country of Holmdel Township, New Jersey, about an hour south of New York City. On top of it, since 1959, stood a strange piece of equipment, a horn reflector antenna 20 feet long, built of aluminum panels, opening its wide mouth to the sky. It had been built for a NASA project called ECHO, which involved bouncing radio signals off large reflective balloons in low orbit. That project had run its course. The horn now belonged to Bell Telephone Laboratories, and it was, in the early 1960s, one of the quietest radio receivers on Earth. Into that quiet came two young men. Arno Penzias, born in Munich in 1933, had been sent as a small child, along with his brother, to England on the Kindertransport, and had eventually made his way to America. Robert Wilson, born in Houston in 1936, had come up through Rice University and Caltech, and had a builder's mind, patient and methodical. Both were radio astronomers by training. Both had come to Bell Labs to use the horn for a scientific purpose. They wanted to measure the faint radio emission of the Milky Way, and to do that properly they needed to know, with great precision, exactly how much noise their instrument itself was producing. So they began, in early 1964, to characterize the antenna, to measure in effect its silence. And they found, when they looked closely, that it was not quite silent. There was a hiss. The hiss was small, it was steady. It did not vary with the time of day, or with the season, or with the direction the horn was pointed. It came in from every patch of sky they tried, at the same faint level, a background whisper that would not go away no matter what they cleaned, replaced, or corrected. And when, after the pigeons had been evicted, and the aluminum scrubbed and the calculations run and rerun, they finally spoke on the telephone to a group of theorists at Princeton who had been sitting down, at that very moment, to design an instrument to search for exactly this signal, the meaning of the whisper became clear. It was the sound of the universe, cooled by 14 billion years of expansion to a temperature just a few degrees above absolute zero, arriving at last at a horn on a hill in New Jersey. And the sky, it turned out, was almost the same everywhere. Almost. Hold that word for a moment. It is doing an enormous amount of work. The cosmic microwave background, the light that filled the young universe when it first became transparent, the oldest photons any instrument will ever see, was, at first measurement, uniform. Point the horn one way, get the hiss. Point it another way, get the hiss. Wait 6 months for the Earth to swing around to the other side of the Sun, point it in yet a third direction, and get, to the accuracy anyone could then measure, the same hiss. A whole sky, glowing at the same faint temperature, without noticeable feature. It looked, from that first measurement onward, as if the universe had been prepared with astonishing evenness, as if some vast hand had smoothed it flat before setting it in motion. The exact number, when it was finally pinned down, was 2.7 to 48 Kelvin, 2 3/4 degrees above the coldest possible cold, a temperature at which the atoms of any ordinary gas would have long since given up any pretense of motion. The whole night sky, glowing at that temperature in every direction, in the microwave part of the spectrum where no human eye could ever hope to see it. Let that settle. The universe, in its background radiation, is a very nearly perfect blackbody at a very nearly uniform temperature. That fact alone, the flatness of that spectrum, the sameness of that sky, is one of the strongest single pieces of evidence any science has ever produced for anything. It matches, to a precision of a few parts in 100,000, the prediction of a hot early universe cooling as it expanded. It is the closing of a very long circle that began with Lemaitre's abominable physics and Hubble's careful photographs on a mountaintop in California. But it is the word almost that concerns us now, because when the instruments grew fine enough to see past the sameness, past the flatness, past the great smooth blanket of primordial glow, they found that the blanket had a wrinkle. The wrinkle had a particular shape. One half of the sky was a little warmer than the average, the other half was a little cooler, and the warm half and the cool half were exactly opposite one another, arranged like the two poles of a magnet across the whole dome of the heavens. In one direction the ancient light arrived slightly bluer, slightly hotter. In the opposite direction slightly redder, slightly colder, a dipole, a pattern with two poles, and a smooth gradient between them. That is a very particular pattern. It is not the sort of thing you would expect from the early universe itself. The early universe, as best anyone could reconstruct, had no reason to prefer one direction over another. The theory said it was born uniform. The measurements said it looked uniform to a very high standard. Why then should there be one direction warmer than all others, and one direction cooler, opposite it, as neatly as a face and the back of a head? There is a very, very old, very simple answer to that question, and it belongs to the 19th century physicist Christian Doppler, who observed that the pitch of a passing train's whistle rises as it approaches and falls as it retreats. Light, being a wave, behaves in the same way. A source of light coming toward you appears bluer than it truly is. A source moving away appears redder. The effect is small at everyday speeds, but for a large enough velocity it becomes measurable. And if you were moving through a bath of light that was truly uniform, at rest with respect to that bath, you would see it as uniform. If you were moving through the same bath, the light ahead of you would come in slightly blue-shifted, hotter, and the light behind you slightly red-shifted, cooler. A perfect dipole, exactly as observed, would fall out of your motion like a shadow falls out of a lamp. The wrinkle in the sky, in other words, was not a property of the sky. It was a property of the observer looking at it. Let me try once more to give you a feel for what that means. The universe hands us a background of light, a great faint glow left over from its earliest transparent moment. That glow is, to a very high standard, the same in every direction. It defines, without asking permission, a frame, a natural rest with respect to the average matter of the cosmos. Anyone moving through space with respect to that frame sees the background take on a lopsided colour, warmer ahead, cooler behind, in exactly the pattern of a stationary bath viewed by a swimmer. The size of the lopsidedness tells you the size of your motion. The direction of the hot pole tells you the direction of your motion. The universe, having refused since Einstein to name a preferred rest, has quietly handed physics a speedometer and a compass, built into the sky. That is the fact this section is about. But between the recognition that such a signal ought to exist and the measurement of it with any precision lay 2.5 decades of very hard engineering. The first hints came before the theory was even fully organised. In 1969, a young radio astronomer named Edward Conklin, working from Stanford, published in the journal Nature a paper suggesting that the cosmic microwave background was not quite the same on all sides, that there was, buried in the noise of ground-based receivers, a small directional variation of about the right size to be a Doppler dipole. It was a difficult measurement. The atmosphere itself glows faintly in the microwave, and the ground beneath the telescope glows more, and the receiver electronics glow, and separating a few thousandths of a degree of cosmic anisotropy from all of that terrestrial warmth required patience and cleverness in equal measure. 2 years later, another observer, Paul Henry, produced a further measurement in the same direction. By the middle 1970s, dedicated experiments carried on high-altitude balloons and mounted on the back of a modified U-2 aircraft had confirmed the effect and begun to sharpen it. The sky had a dipole. It was not an artifact. It was of the size the Doppler interpretation predicted. And it pointed, roughly, in a direction that would come to feel oddly domestic once you knew where to look. But atmosphere is atmosphere, and even at the top of the troposphere there is still air overhead, still water vapour, still the faint residual glow of a warm world beneath. To measure the sky properly, one needed to leave the sky. One needed to send an instrument into orbit and let it drink in the microwave background from above the atmosphere entirely, with the whole Earth reduced to a bright disk behind a shield. That instrument, when it was at last built, was called COBE, the Cosmic Background Explorer, a satellite in the shape of something like a squat cylinder wrapped in a conical sunshade, its instruments looking outward from behind a shield of insulation, kept cold by the geometry of its orbit and the careful arrangement of its shades. It was a NASA mission, put together over the course of the 1980s by teams scattered across universities and government laboratories. It carried 3 principal instruments. One, called FIRUS, the Far-Infrared Absolute Spectrophotometer, was designed to measure the spectrum of the background across a wide range of microwave wavelengths to see whether it truly matched a blackbody or whether it deviated in any small detail. Its lead investigator was John Mather, a young physicist at NASA's Goddard Space Flight Center in Maryland, patient and quiet, who had been working toward exactly this measurement for most of his professional life. Another instrument called DMR, the Differential Microwave Radiometer, was designed not to measure the average temperature of the sky, but to compare very finely the temperature of one small patch to the temperature of another. Its lead was George Smoot, at the Lawrence Berkeley Laboratory in California, whose interest ran to the largest structures and the faintest imprints. The satellite was launched on the 18th of November 1989 from Vandenberg Air Force Base on the coast of California aboard a Delta rocket. It climbed into a nearly polar orbit some 900 kilometres above the Earth, arranged so that its sunshade could keep the sun and the Earth permanently on one side while its instruments looked coldly away into deep sky. And then it began, for the next 4 years, to scan. The results, when they came, arrived in 2 waves that between them rearranged the map of what the early universe was known to be. The first wave was FIRUS. In January of 1990, at a meeting of the American Astronomical Society, John Mather presented the instrument's first spectrum of the cosmic background. It had been assembled from just 9 minutes of data. He put a graph on the screen. The graph showed the predicted blackbody curve as a smooth line, and the FIRUS measurements as points along that line. The points in the line were indistinguishable. The measurement error bars were smaller than the thickness of the line itself. The audience of astronomers, who had been prepared over decades to expect a good match, had never seen a match like this. They rose to their feet and applauded a graph. The cosmic microwave background, to a precision of about 3 parts in 10,000, was a perfect black body at a temperature of 2.725 Kelvin. The prediction of a hot early universe cooling as it expanded was confirmed to a standard no other cosmological measurement had ever approached. The applause was for the ordinariness of the picture. The universe had a spectrum, and the spectrum was exactly what the theory said, and there was nothing more in that particular graph to argue about. The second wave was DMR, and it took longer. Comparing tiny temperature differences from patch to patch of sky is a subtle business, and George Smoot's team spent nearly 2 years pulling their data apart and putting it back together, checking for every conceivable source of instrumental error before they were willing to say publicly what they saw. When at last, in April of 1992, they announced their result, they announced two things at once. The first was that once you subtracted the dipole, the great two-lobed warm and cool pattern that dominated the low-order variation of the sky, the remaining background was uniform to a level of about 1 part in 100,000. The universe, on its largest scales, had been born nearly featureless, and yet, buried in that near-featurelessness, DMR had detected the beginnings of features, fluctuations of a few tens of millionths of a degree, patches slightly warmer and slightly cooler than average, spread across the sky in a pattern consistent with the first stirrings of the structure from which galaxies would later grow. Smoot, at the press conference announcing the discovery, said famously, and in retrospect perhaps a little too warmly, that if you were religious, it was like looking at God. What he meant was that this was the earliest, faintest imprint of the seed pattern from which every galaxy and cluster in the visible universe had eventually condensed. Both men, Mather for the perfect spectrum, Smoot for the earliest structure, would share the Nobel Prize in Physics in 2006. But for our purposes, tucked inside that same COBE data was the other thing, the dipole, the pattern that had to be subtracted cleanly and carefully before the rest of the small structure could be seen. In the language of the mission, the dipole was a systematic, a large signal that had to be removed to expose the smaller signals beneath it. It was a nuisance in a certain sense for the cosmologists interested in the primordial fluctuations, but it was itself a measurement, and it was the most precise measurement of its kind that had ever been made. The dipole, COBE said, had an amplitude of about 336 to 337 millikelvin. That is, the hottest point on the sky, in the microwave background, was about 3 1/3 thousandths of a degree above the average. The coldest point, opposite it, was about 3 1/3 thousandths below. In the direction of the hot pole, the ancient light arrived slightly blue-shifted. In the direction of the cold pole, slightly red-shifted. The hot pole lay in a particular part of the heavens, a patch high in the springtime northern sky, in the constellation of Leo near the boundary with a fainter neighbouring constellation called Crater, the Cup. Toward the Cup, the universe glowed a whisper warmer, away from it, a whisper cooler, and the size of that whisper, translated by the Doppler formula, gave a speed. Let me put that speed carefully. The solar system, on the interpretation the COBE team laid out and every subsequent measurement has refined, is moving with respect to the frame in which the cosmic microwave background is most uniform at a velocity of about 370 kilometres per second. The best modern number, from later missions with finer instruments, the Wilkinson Microwave Anisotropy Probe, which flew in the 2000s, and the Planck satellite, which flew in the 2010s, is very close to 369.82 kilometers per second, with an uncertainty of about 100 meters per second. It is that steady, and it is that well measured, 370 kilometers every second toward that patch of sky at the border of Leo and Crater. Say that number slowly, 370 kilometers per second. Consider what that means with your body. You have perhaps driven across a country, or watched from an aeroplane window as a coastline unrolled beneath you. The continental United States, from the beaches of California to the beaches of Massachusetts, measures a little over 4,000 kilometers end to end. A car crossing it at highway speed takes the better part of a week. A jet crosses it in 5 or 6 hours. Light itself needs about 14 milliseconds, and the whole solar system, the Sun, the Earth beneath you, the Moon, Mars, Jupiter, Saturn out to Pluto and beyond, is drifting through the great average frame of the universe at a rate that would carry it from one American coast to the other in a little under 12 seconds, roughly the time it takes to draw and release 3 slow breaths. In the space of one exhalation, the entire ordered machinery of our home star has moved, with respect to the average matter of the cosmos, farther than any human being has ever travelled on foot in a day. Rest with that for a moment. The chair holds you still. The floor beneath the chair holds still. The house holds still. And yet, at this instant, the whole neighbourhood, the whole country, the whole planet, the whole solar system, the sun with all its attendant worlds, is sliding through the ambient photons of the universe at a rate that would consume a continent in a dozen heartbeats. This is what the wrinkle in the sky is telling us. Not that the early universe was uneven, not that the Great Glow was born lopsided. The Great Glow was born as smooth as the theory needed it to be. The lopsidedness is us. The lopsidedness is the shadow of our motion falling across a perfectly still bath of light. When we subtract the dipole from the code map, what we are really doing is transforming into the rest frame of that bath, mathematically stepping off our own moving platform onto the platform of the universe as a whole. And when we look at the sky from that stepped-off vantage, it becomes uniform again to a part in 100,000, and the primordial structure emerges, faint and delicate beneath. There is a philosophical vertigo in this that repays some attention. Einstein's principle said, and still says, that no inertial frame is fundamentally preferred. All are equally good for the writing of physical law. The dipole in the cosmic background does not overturn that. The frame in which the CMB is most uniform is not preferred by the laws of physics. The laws work identically for any observer, however she is moving. But that frame is preferred by the contents of the universe. It is the frame in which the great average of all the matter and radiation of the cosmos is, in the aggregate, at rest. It is a frame the universe happens to offer, freely, once anyone has an instrument fine enough to see it. And once you have seen it, you know something you did not know before about where you stand. You know that you are moving, not in the trivial sense of the earth turning under your feet, though it does. Not in the ordinary sense of the earth swinging around the sun once a year, though it does. Not in the astronomical sense of the sun looping around the centre of the galaxy, though it does. In a further, deeper, larger sense than any of those. Above and beyond and around all those familiar motions, added onto them at some level, and largely swallowing them at another, is this: 370 kilometres per second toward Leo, toward the cup. A velocity for the whole solar system measured against the oldest light in existence, and this is where the honest question begins to sharpen. 370 kilometres per second is a large number. It is much larger than the Earth's rotation, which at the equator carries a person along at less than half a kilometre per second. It is much larger than the Earth's orbit around the Sun, which is a respectable 30 kilometres per second and no more. It is roughly comparable to, but rather larger than, the speed at which the Sun swings around the centre of the Milky Way, which is somewhere in the range of 230 to 250 kilometres per second. Something is producing a velocity for us that is not merely the sum of the familiar orbits. Something is carrying our whole neighbourhood, the Sun and its planets, the nearby stars, the local corner of the galaxy, in a direction that has nothing to do with the tidy arithmetic of turning on our axis and looping around a star. What is it? Is it one motion, or many, layered on top of each other and producing this net drift by their combination? Is there a single great river we are being carried on, or a set of nested currents whose sum, when honestly added, comes to this figure? The dipole is a single number and a single direction, but we already know that we are participating in at least several motions at once. The Earth spins, the Earth orbits, the Sun orbits. The galaxy itself is not stationary, but drifting through its own small neighbourhood of galaxies. That neighbourhood in turn is falling towards something, and that something is falling towards something else. The universe hands us a speedometer. The speedometer reads 370. It does not itself say what set of motions produced that reading. To answer that, one has to unpick the sum. One has to take the single arrow that points from the solar system toward the cup and decompose it, patiently, into all the smaller arrows that add up to make it: the rotation, the orbit around the Sun, the Sun's long slow circuit through the arms of the galaxy. The galaxies drift through the local group. The local groups fall towards something enormous in the direction of Centaurus, and possibly other motions still, on scales larger than any of those. We know the total. We can measure it to a fraction of a percent. The question, the whole question of the second half of this story, is what the total is made of. Which of these currents is largest? Which is smallest? Are they all pulling more or less in the same direction, so that their sum is nearly the largest of them? Or are they arranged more mysteriously, so that a big motion is partially cancelled by another big motion, leaving a net that is smaller than any single component? What does it mean that the Sun's orbit around the galaxy runs at roughly 240 kilometers per second, but the whole solar system's motion through the cosmic frame runs at 370? Does the galaxy itself drift in a direction that adds to the Sun's orbital speed, or in one that subtracts from it? And when we have accounted for the galaxy, and the local group, and the great fall toward the Great Attractor beyond, does the arithmetic close? Do all the currents sum at last to the arrow the code dipole draws for us? Or is there residual motion, unaccounted for, pointing at some further and even larger structure we have not yet named? Those are the questions that carry us out of the introduction of the speedometer and into its careful reading. The speed is settled, 370 kilometers per second toward the cup. The direction is settled. The layers beneath that number are what the rest of this story is about. Settle in for that. The sky above you is, at this moment, a fraction of a thousandth of a degree warmer in one direction than in another, and the difference is you. Every breath you draw, the whole planet moves the width of a small city through the ancient bath of light. And beneath the smooth arrow of that motion, a stack of separate currents is at work. Some familiar, some strange, some only recently mapped, each contributing its own share to the final velocity. To understand the number is to unpick the stack, layer by layer, from the smallest and closest to the largest and most distant. The first layer, and the one you can feel most easily, is the one you are standing on. Consider, then, the earth beneath you. It is turning. It has always been turning, in every moment of your life, in every moment of every life before yours, and the turning is so smooth and so continuous that no organ in your body has ever registered it as motion. If you are near the equator, the ground you stand on is moving eastward at roughly 465 meters every second. That is close to half a kilometer. In the time it takes you to draw one long, slow breath, the piece of earth under your feet has slid the length of several city blocks through space, and you have gone with it, and the coffee cup on your table has gone with it, and the room, and the walls, and the whole quiet architecture of the ordinary hour. If you are further from the equator, closer to one of the poles, that speed drops with the cosine of your latitude. At mid-latitudes it is nearer 300 meters per second. At the poles it approaches zero. A person standing exactly on the geographic pole would, in a rotational sense, only pivot on the spot, like a dancer turning slowly in place across a day. 465 meters per second sounds fast when written down. In context, it is almost nothing. It is a whisper. It is the first and smallest of the layered currents we are trying to identify, and against the 370 kilometers per second we are trying to account for, it is less than a fifth of 1%. It is a rounding error in the great arithmetic of cosmic motion, but it is the layer you can feel if you know how to look for it, in the eastward drift of clouds, in the slow curve of long-range weather systems, in the small correction pilots make on transcontinental flights. It is the layer that gives you day and night. It is the layer that carries the sunrise across the face of the world at roughly the speed of a passenger jet. Small as it is real, and it is where the accounting begins. Peel that back. Set the spinning of the earth aside for a moment. Now consider that the earth, whether spinning or not, is falling. It is falling around the sun. Falling is the honest word for it. The whole of orbital mechanics is at bottom, a story about objects that are permanently falling and permanently missing the thing they are falling toward. The Earth's fall is a nearly circular one, at an average distance of about 150 million kilometers from the Sun, and to keep that fall stable it must travel very quickly indeed. Roughly 29 3/4 kilometers every second, nearly 30. In the time it takes you to say the word orbit, aloud, and slowly, the planet has moved something like 60 kilometers along its path. In the time it takes you to finish this paragraph, it has moved further than the distance between most neighboring cities. Say that number slowly, 29.78 kilometers per second, 66 times faster than the equatorial rotation. This is the second layer, and already the first has almost vanished by comparison. If you were somehow able to stop the Earth's orbit and leave only its rotation, the planet would drift free of the Sun, and you would notice within a season. If you were able to stop only its rotation and leave the orbit, you would lose the alternation of day and night, but you would still be riding the same fast river around the same warm star. That fast river is the second component of the arrow. It is, in its own way, a familiar one. Every schoolroom orrery makes it visible, every calendar depends on it, and yet almost no one in the middle of an ordinary afternoon thinks of the planet as a moving thing. The stillness of the room is so persuasive that it swallows the fact of a 30 km per second fall. That is the trick of every well-behaved motion. The steadier it is, the less it registers. The car on a straight, smooth motorway feels almost stationary until you glance at the windscreen. The Earth, on the smoothest and steadiest track imaginable, feels stationary always. Peel that layer back too. Set aside the spin, set aside the orbit around the Sun. Now consider the Sun itself. The Sun is not fixed. It is not the still centre Copernicus once needed it to be. Copernicus's great correction was to move the Earth out of the middle of things, and to put the Sun there instead, and for a certain kind of local astronomy that was a decisive step. But in the larger frame, the frame in which the Milky Way is a rotating spiral of hundreds of billions of stars, the Sun is one of those stars in a middling location on a slow, enormous circuit around the galactic centre. It carries the whole solar system with it. The Earth, the Moon, the other planets, the asteroid belt, the comets in their long cold orbits, all of them, together, ride the Sun's ride. The centre of that ride is a place we now know is anchored by a single enormous object, a supermassive black hole named Sagittarius A star, roughly 26,000 light-years from where you are sitting. The stars of the Milky Way do not orbit it as neatly as planets orbit a sun, because the mass of the galaxy is spread across an enormous disk, rather than concentrated in a single point. Most of what holds the Sun on its circuit is the collective gravity of everything inside its orbit. The stars, the gas, the dark matter, the whole vast weight of the inner galaxy. But Sagittarius A star sits at the geometric heart of that weight, a gravitational marker, the still small point around which the Great Wheel turns. The Sun's speed on that wheel is one of the harder numbers in this story to pin down. The best established reference figure, the one that appears in the standard textbooks of galactic dynamics, is about 220 kilometres per second. Some measurements push it a little higher, toward 230, or even 240. The honest answer is that the number carries an uncertainty of perhaps 10%, 20 kilometres per second either way, because measuring the motion of the Sun around a centre we cannot directly see, using stars whose own motions are complicated, is genuinely difficult. This is, in fact, the largest single source of uncertainty in the whole layered accounting we are trying to build. The smallest layer, the equatorial rotation, is known to a fraction of a metre per second. The layer of the Sun's galactic orbit is known to something like the width of a city on the speedometer. But even at the lower estimate, 220 kilometres per second is a staggering number. It is roughly 7 times the Earth's orbital speed. It is nearly 500 times the equatorial rotation. In the time it takes you to draw a single breath, the Sun and everything with it have moved more than 1,000 kilometres along the galactic track. In the time it takes to read a paragraph of this narration, they have moved further than the diameter of the Earth. And this motion is so smooth and so far removed from anything a human sense can register that for almost all of history no one suspected it at all. The Sun looked fixed. The stars looked fixed. The truth is that both are on the great slow wheel, and the wheel is turning. Let that settle. The 3 layers so far, spin, orbit and galactic circuit, already span 3 orders of magnitude, half a kilometre per second at the smallest, 30 at the middle, 220 or so at the largest, and already the third of those is comfortably more than half of the total we are trying to account for. The galactic orbit alone accounts for the majority of the arrow the CMB dipole draws for us. The first 2 layers, added to it, would only shift it by a fraction of a percent in one direction or another, depending on the moment. How long does one full circuit of that great wheel take? Long enough that the question is almost a category error. The Sun's orbit around the Milky Way's centre takes something between 225 and 250 million years, depending on how you count. Astronomers sometimes call one such circuit a galactic year, or a cosmic year. It is a unit of time so vast that the ordinary calendar becomes meaningless inside it. A human life is not a rounding error against a galactic year. It is smaller than that. A whole recorded human history, from the earliest writing to the present moment, occupies less than 1 part in 50,000 of a single circuit. The Sun has, in the entire lifetime of the Earth, completed only about 20 full orbits of the galaxy. 20. Fewer than the fingers and toes on 2 people. Rest with that for a moment. The last time the solar system occupied its present position in the galaxy, the last time it stood, so to speak, exactly here on the Great Wheel, was somewhere around 225 to 230 million years ago. That is deep in the Triassic. The continents were not where they are now. There was in fact one great continent, Pangaea, only beginning to break apart. The seas were populated by creatures whose descendants are long extinct. On the land, the very first dinosaurs were only just appearing, small, agile, unpromising animals whose lineage would go on to dominate the planet for the next 160 million years and then, almost entirely, vanish. The rise and fall of the dinosaurs from their first tentative appearance to the asteroid that ended them took less than 1 galactic year. The whole story of mammals, from tiny nocturnal survivors to the great herds of the plains, to the species now reading and listening to this sentence, has unfolded inside a fraction of a single further circuit. The sun has not yet completed one full turn since the last dinosaur died. That is the timescale of the third layer. That is what it means to say the sun moves at 220 kilometers per second around the center of the galaxy. The number is enormous, and yet the circuit is so vast that the enormity almost cancels itself. The sun is a very fast runner on a very slow track. Where is the sun on that track right now? Not near the center, not far out toward the edge. It sits about 2/3 of the way from the middle to the visible rim, in a region of the disk that is neither one of the great crowded spiral arms, nor one of the emptier spaces between them, but a smaller feature, a spur or a minor arm called the Orion Arm. It is a modest piece of galactic scenery, tucked between two larger arms named for the constellations Sagittarius and Perseus. The sun's neighborhood, on the scale of the whole galaxy, is unremarkable. There is nothing at this location that would draw the eye of a distant observer. That, too, is part of the pattern. The story of humanity's changing address in the universe has been, again and again, a story of finding that no location is special. Not the Earth, not the sun, not even the sun's small quiet lane inside the galaxy. Now peel that layer back as well. Consider the galaxy itself. It, too, is not fixed. It moves. And here the accounting shifts from motions we can, in principle, feel, spin, orbit, the great slow wheel, to motions of a different order altogether. The Milky Way drifts through a small neighborhood of galaxies, the local group, which is bound together by mutual gravity into a single loose collection of roughly 50 or so members. The two great members of that group are the Milky Way itself and the Andromeda Galaxy, catalogued as M31, which sits about 2.5 million light-years away. Around those two dominant spirals are strung dozens of smaller companions, dwarf galaxies, satellite galaxies, the Magellanic Clouds among them, orbiting and drifting and occasionally being swallowed. The whole ensemble spans something like 10 to 17 million light-years across, a modest neighborhood by cosmic standards, but a neighborhood large enough that light itself takes millions of years to cross it. Andromeda has been noticed and named and puzzled over for a very long time. The Persian astronomer Abd al-Rahman al-Sufi wrote it down in the 10th century, describing it as a small cloud in the sky. For centuries after, it remained a smudge, one of many nebulous patches whose nature was not settled until Edwin Hubble, at the 100-inch telescope on Mount Wilson in the 1920s, measured a Cepheid variable inside it and proved that it was not a nebula at all but a separate galaxy, an entire island of stars beyond our own. And Andromeda is not standing still relative to us. It is approaching. The Milky Way and Andromeda are drifting toward each other at something in the neighborhood of 110 to 120 kilometers per second, on a trajectory that will, in some 4 or 5 billion years, bring them into a first close encounter and eventually into a full merger. That merger has, in the popular retelling, been assigned a date. 4.5 billion years, give or take. In the honest telling, the number carries wide uncertainty. More recent simulations, using better measurements of Andromeda's sideways motion, allow scenarios in which the collision is delayed, or in which the two galaxies pass close by each other several times before finally settling into one. There is even a possibility, given the ranges of uncertainty involved, that the merger takes 10 billion years, or that it never quite fully closes. What is not in doubt is that the two are moving toward each other, and that on the timescale of the sun's lifetime the encounter is coming. That fact alone is worth pausing on. Even galaxy-scale objects 100,000 light-years across containing hundreds of billions of stars, are in motion. They drift, they are drawn, they can be pulled toward one another, and on the long, slow scale of cosmic time they can merge. Nothing in this story is fixed. The wheel turns, the galaxies drift, and even the neighborhoods to which the galaxies belong are moving through something larger. Which brings us to the next layer of the accounting. If the Milky Way is moving through the local group, and it is, and if the local group as a whole is drifting through some larger space, then to arrive at our motion relative to the cosmic rest frame, we have to add that bulk motion to everything already tallied. When astronomers do the sum honestly, they find that the local group itself has a bulk velocity of something like 627 kilometers per second, relative to the cosmic microwave background, larger, in fact, than any single galaxy's motion within the group. The individual motions of the Milky Way and Andromeda tumbling toward each other are set within a much larger current that carries the whole neighbourhood, together in one shared direction. That is the strange arithmetic of the layered stack. The Sun's galactic orbit runs at around 220. The Milky Way's motion within the local group is smaller than that. The local group's bulk drift is larger than either, and when all of these arrows are added, honestly, with their proper directions, some reinforcing, some cancelling, the sum, as measured against the ancient bath of light, comes out to 370 kilometres per second, toward the cup, toward Crater, toward the border with Leo. The number closes more or less when the accounts are settled. The residual, whatever cannot be explained by the motions we have named, is small, but it is not zero, and its direction is what forces the story onward. Because the direction of the local group's bulk drift is not toward anything obvious. It does not point toward any single bright galaxy or any well-known cluster. It points instead toward a region of the sky in the direction of the constellations Centaurus and Norma, and much of that region is inconveniently, almost mockingly, hidden. Hidden behind the disk of our own galaxy. The Milky Way's own dust and stars, seen edge on from inside, form a bright dense band across the sky. The band you can still, on a dark enough night, see arching overhead. And behind that band, in the direction of Centaurus and Norma, there is a stretch of sky that optical telescopes simply cannot penetrate. Astronomers call it the zone of avoidance. It is the shadow our own home casts on the deeper universe. And somewhere behind that shadow, the accounting insists, there is a mass. A very large one, large enough to pull a whole supercluster of galaxies, including ours, toward it. Large enough to leave its fingerprint in the peculiar motions of galaxies across hundreds of millions of light years. The first people to see that fingerprint clearly were a small collaboration of astronomers in the late 1970s and the 1980s. 7 of them in the end. Alan Dressler, Sandra Farber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Turlevich, Gary Wegner. They called themselves, half in earnest and half in affectionate joke, the Seven Samurai, a nod to Kurosawa's film and to the reputation the group had acquired for going after ambitious, sometimes unfashionable questions with a certain stubborn confidence. They were interested in a very specific problem: how to measure the distances to elliptical galaxies without having to rely on the general expansion of the universe as a yardstick. If you could measure the distance to a galaxy independently, then compare it to how fast the galaxy appeared to be receding, any discrepancy would be the galaxy's peculiar velocity, its own motion, above and beyond the smooth flow of cosmic expansion. And if you did that for enough galaxies, in enough directions, you could map the invisible currents beneath the Hubble flow. Their method used a relationship they helped establish, called the dn sigma relation, which linked the physical size of an elliptical galaxy to the velocity dispersion of the stars inside it, the width of the range of speeds at which those stars are wandering around the galaxy's centre. Faster internal motions meant larger, more massive galaxies. Larger galaxies at a given apparent brightness meant they must be closer than you would otherwise assume, or further. It was a way to sidestep the general expansion and get at intrinsic distances. Applied to roughly 400 ellipticals scattered across the sky, it gave them, at last, a map of peculiar velocities. What that map showed was extraordinary. It was not chaos. It was not a random scattering of small motions in every direction, cancelling out into nothing. It was a coherent flow. Across an enormous volume of space, galaxies were streaming together in the same general direction. The Milky Way, the local group, the whole of the local supercluster, all moving, all sliding in one shared river, and the river was pointed toward the same region behind the zone of avoidance that the CMB dipole's residual had suggested. Centaurus, Norma, something huge, hidden behind our own galaxy's dusty band. Alan Dressler gave it its name, the Great Attractor, 2 words chosen for their weight and their frankness, both accurate. Great, because whatever it was, it had to be enormous, containing something like 10 to the 16th solar masses in the early estimates, more than any single cluster then known. Attractor, because it was pulling. It was drawing our whole cosmic neighbourhood toward itself at speeds that, when finally tallied, approached 600 kilometres per second, more than 2 million kilometres per hour, and it was doing so from a distance of somewhere between 150 and 250 million light-years, near enough that its pull could be felt clearly, far enough that its identity was at first almost entirely mysterious. The reception, when the Seven Samurai's results began to appear in the astrophysical journals in the mid-1980s, was not uniformly welcoming. The prevailing picture of the universe at that scale was of something smooth, homogeneous, a gentle Hubble flow with only small perturbations. To claim that a coherent stream of galaxies, spanning a substantial fraction of the observable local universe, was being dragged toward a single hidden concentration of mass that ran against the grain of what many cosmologists then believed the larger scales should look like. There was skepticism, there were counter-analyses, there were for years disagreements about the size of the effect, the location of its source, and even whether it was real. But the effect did not go away, it sharpened. Better surveys, better distances, better maps of peculiar velocities all confirmed the same broad picture. Something enormous in the direction of Centaurus and Norma was reaching out across 150 million light-years and gently, insistently, pulling us in. And behind the Great Attractor, the story would eventually reveal there was something else again, a still larger concentration further away, adding its own contribution to the flow. But that is a piece of the story for later. For now, at the end of this layer of the accounting, the picture stands like this. The sun turns, the Earth spins and orbits, the whole solar system rides the great wheel of the galaxy. The galaxy drifts through its local group. The local group falls, together with much of the local supercluster, toward a hidden mass whose full nature is only now being mapped. And when all of those motions are added, honestly, they nearly close on the arrow the ancient light draws for us. Nearly. Not quite. There is still a little further to go. A little further to go and a little further to look. Because for a long time the Great Attractor was the end of the sentence. It was where the arrow pointed, and it was where the mass appeared to sit, and the residual after subtracting our own galaxy's rotation, and the local group's motion seemed to be mostly accounted for by that hidden concentration behind the dust of Centaurus. Mostly. There was always a small excess, a slight extra push, or pull, that the Great Attractor alone could not comfortably explain. And as the surveys deepened, as more distant galaxies were mapped, and their peculiar velocities measured with more care, the excess did not fade, it grew more articulate. Something further out was contributing, something beyond. That something, when it began to show its face in the data, turned out to be another concentration of mass, further along the same general line of sight but much deeper into the universe. A denser knot of galaxies at a distance of several 100 million light-years, well beyond the Great Attractor, contributing its own gravitational tug to the same broad flow. The name given to that further concentration is the Shapley supercluster, after the American astronomer whose early surveys of the southern sky had noted decades before an unusual richness in that direction. And when the peculiar velocity measurements were refined enough to disentangle the two, the picture that emerged was of a nested pull, the Great Attractor near, the Shapley further, both drawing us in the same direction, both contributing to the same river of coherent motion. That could have been the end. A tidier story with two attractors instead of one, the numbers finally closing, the arrow finally explained. But the story was not tidy yet, because the map itself was still only half a map. Astronomers had been very good for a long time at charting the places where matter is, where galaxies gather, where light concentrates. What they had been slower to chart, because it is harder, is the places where matter is not, the empty regions, the vast, quiet volumes of the cosmic web where galaxies thin out and, over enormous stretches, almost disappear. And that is where the last piece of the accounting finally arrived, and where the story, in some sense, resolved. The team was familiar. R. Brent Tully, at the University of Hawaii, who had spent much of a career mapping the nearby universe in 3 dimensions. Hélène Courtois, at the University of Lyon. Yehuda Hoffman, at the Hebrew University of Jerusalem. Daniel Pomered, at the CEA Paris-Saclay. 4 researchers whose collaboration had been steadily reshaping the way our cosmic neighbourhood was drawn. In September of 2014, in the pages of Nature, they published a paper that changed the address of the human species. The paper's central idea was quiet, almost technical, and enormous in its consequences. Instead of drawing a supercluster the old way, a smudge on a map, a rough cloud of galaxies grouped by proximity, they proposed drawing it by flow. They took the peculiar velocities that the 7 samurai and their successors had spent decades measuring, and they asked a very simple question. If you follow the streamlines, if you trace where each galaxy is being pulled by the summed gravity of everything around it, where do the streams converge? Where does the water in this particular basin drain? That is what a supercluster is, they suggested, if you take it seriously as a physical object. Not a cloud of galaxies drawn on a map, but a watershed. A region of space within which everything is falling, together toward a common gravitational floor. When they drew the boundary of our watershed, it enclosed a volume roughly 520 million light-years across. It contained something on the order of 100,000 large galaxies. Its mass, integrated over that volume, came to something like 10 to the 17th solar masses, 100 million billion suns, an amount that is easier to say than to feel, and near its centre of mass, gathering the flow of the entire structure into itself, sat the Great Attractor. They gave the structure a name, Laniakea, a Hawaiian word in honour of the Polynesian navigators who read the sky as an inheritance and a chart at once. It means immense heaven, spacious heaven, and the naming, once you sit with it, is the point, because what Tully and his colleagues had done was not to discover a new object in the distance. They had discovered where we live. They had drawn the walls of the room we are inside. Brent Tully described what it felt like in the plainest possible words. This, he said, is not unlike finding out for the first time that your hometown is actually part of a much larger country that borders other nations. All the astronomy that had come before had been, in that image, local geography, your street, your neighbourhood, your city. Laniakea was the country, the Milky Way and the local group and the Virgo cluster and the Great Attractor and everything falling together in that same coherent river. All of it turned out to be one thing, with an edge, with neighbours on the other side of the edge. A political map drawn for the first time of the cosmic scale on which our motion actually happens. And then, 3 years later, the same team published again and completed the picture. Because if Laniakea explained where we are falling, it did not yet explain the whole of why. The Great Attractor pulled. The Shapley supercluster further along pulled more. Together they went a long way toward accounting for the 630 kilometres per second at which the local group is drifting through the CMB frame. But not quite the whole way. There was still, in the honest accounting, a little extra motion, a little extra push, whose source was not obvious in any concentration of mass yet mapped. Hoffman, Pomered, Tully, and Courtois asked a question that, in retrospect, is almost embarrassingly simple. What if the missing contribution is not a pull at all? What if it is an absence? The universe, at the larger scales, is a web. Threads of galaxies strung along filaments, denser knots where the filaments cross, and between them, enormous, nearly empty regions, voids, places where the density of matter is far below the cosmic average, not merely thinner, but strikingly structurally thin, hollowed out over hundreds of millions of light-years. And here is the quiet gravitational fact. In a universe where the average density is what it is, a region that is emptier than average behaves in the arithmetic of gravity as if it were pushing. Not because empty space exerts a force, it does not, but because everything around it is being pulled, more strongly, by the denser regions elsewhere. A void, from the point of view of a galaxy sitting near its edge, is a place from which you are being drawn away. And that draw, in the mathematics of peculiar velocities, looks exactly like a push. They mapped the peculiar velocity field with the best data they had. They followed the flows not only toward their attractors but away from their sources, and in the direction opposite to the Shapley concentration, on the far side of the sky from everything that was pulling us in. They found a region that was strikingly coherently empty, a vast underdensity, a hollow in the cosmic web. They named it, plainly and precisely, the dipole repeller. The paper appeared in Nature Astronomy at the beginning of 2017, and what it said, when all the arithmetic was done, was this. The motion of the local group through the CMB frame is not driven by a single attractor. It is not even driven by attractors alone. It is driven by a balance. On one side of us, the Shapley concentration, and closer, the Great Attractor, pulling. On the other side, the dipole repeller, an emptiness so large that its emptiness is felt. The local group is caught gently between a fullness and a void. It slides down the gradient between them at 630 kilometres per second in the direction that the balance dictates. Hoffman put it with the same restraint. In addition to being pulled toward the known Shapley concentration, We're also being pushed away from the newly discovered dipole repeller. Push and pull, he said, are of comparable importance at our location, not a metaphor, an accounting, and with that accounting the numbers finally closed. Sit with what that means for a moment before we bring it home. The arrow that the cosmic microwave background draws across the sky, the arrow that first appeared as a faint dipole in a satellite's data, a millikelvin warmer here and a millikelvin cooler there, is now, at last, entirely legible. It is the sum of your rotation on the Earth. It is the sum of the Earth's orbit around the Sun. It is the sum of the Sun's long, slow ride around the Milky Way's centre. It is the sum of the Milky Way's motion within the local group. It is the fall of the local group down the slope of Laniakea toward the Great Attractor, deepened by the Shapley concentration behind it, tilted by the emptiness of the dipole repeller on the far side. Every one of those layers is a real gravitational relationship with a real piece of the universe, and every one of them, when added, points where the CMB says it should. The universe, in other words, is telling you the truth about where you are, because it is telling you the truth about what you belong to. The dipole in the ancient light is a receipt for a gravitational history. It records the fact that you are inside Laniakea. It records the fact that Laniakea is embedded in a larger flow, sculpted between attractors and voids. It records the fact that all of this structure grew, over billions of years, out of tiny density variations that were themselves already present when that light was released. The map you see when you look at the sky's faintest microwave glow is, in the end, a map of the mass that was there, and of the mass that has moved you since. And now, gently, the philosophical question that has run under every layer of this story finally has its answer. Einstein was right. There is no absolute space. There is no privileged frame written into the fabric of the universe, no invisible scaffolding against which every motion is secretly measured, no hidden truth about which body is really at rest. The bucket that Newton spun does not spin against an unseen absolute. It spins against the total mass distribution of the cosmos, exactly as Mach whispered it might. And yet, the CMB frame is not nothing. It is not a metaphysical cheat. It is the frame in which the matter of the early universe was, on average, at rest. It is a physical fact about a specific configuration of stuff, the plasma of the young cosmos, spread through space almost uniformly, cooling together, releasing its last light together. To measure your velocity against that frame is not to violate relativity. It is to note with precision how your local gravitational history has moved you relative to the rest of the matter that shared your birth. The CMB does not tell you whether you're moving in some cosmic absolute sense. Nothing tells you that, because there is no such sense to be told. The CMB tells you how you are moving with respect to everything else that was there at the beginning. That is a different question, and it is a beautiful one, and the universe answers it. So bring it all back one last time, and let the arithmetic land where you sit. At the equator of the Earth, you are turning at roughly 0.465 kilometers per second. Further from the equator, a little less. This is the smallest of the numbers. It is the speed of a fast passenger jet, and it is the speed at which the ground under your feet is carrying you around the axis of the world. While that rotation continues, the whole Earth is carrying you around the Sun at about 29.8 kilometers per second. Nearly 30 kilometers in every second, without interruption, without pause, in a great slow ellipse that closes on itself once a year. While that orbit continues, the Sun is carrying you around the center of the Milky Way at roughly 220 kilometers per second, a speed that takes something on the order of 230 million years to complete a single loop. In the time since the Sun last stood where it stands now, dinosaurs came and went. While that revolution continues, the whole Milky Way, together with Andromeda and the smaller galaxies of the local group, is drifting through the deeper structure of Laniakea, falling, as a group, down a gravitational slope shaped by attractors and voids. And when all of those motions are summed, honestly, layer upon layer, they come to something very close to 370 kilometers per second, in a direction that the ancient light of the CMB has been quietly pointing at all along. That is your velocity, not against absolute space which does not exist, against the average rest of the matter you were born from. That is your address. Not a street, not a city, not a country, but a supercluster, Laniakea, immense heaven, 520 million light-years across, 100,000 galaxies, 100 million billion suns, and you inside it, alive for a little while at one small point in the flow, And that is your question, the one you began with, when you were sitting still in the chair and it did not feel as though anything was moving. Am I moving? It is the oldest question a body can ask of the sky. Aristotle asked it in his terms, and Ptolemy in his, and Copernicus in his, and Galileo through a lens, and Newton through his bucket, and Mach through his doubt, and Michelson through his mirrors, and Einstein through his patient thought, and Penzias and Wilson through a horn antenna full of hiss, and Tully and Courtois and Hoffman and Pomered through the streamlines of the cosmic web. And the answer that this long chain of asking has finally shaped is not a number, though it contains a number. It is a recognition. To ask, am I moving, is always also to ask, who wants to know? There is no motion without a frame. There is no rest without a witness. Every velocity is a relationship between the thing that moves and the thing against which the movement is measured. And the deepest, gentlest reply the universe has given us to that question is the ancient light itself, a whisper from the first hour of everything, filling the sky, carrying in its faint warmth on one side and faint coolness on the other a record of where you are and where you're being carried. You're moving at roughly 370 kilometers per second, right now, as you rest in whatever quiet room this reaches you in. You're not moving through absolute space, because there is no such space to move through. You're moving through the memory of the beginning. You're moving through the rest of everything you belong to, and the light that tells you so has been on its way to you for nearly 14 billion years, patient the whole distance so that on this one small evening, in this one small body, you could sit still and know, at last, exactly what it means to be in motion. Rest with that. The chair does not move, the room does not move, the earth turns beneath you, and the sun carries you, and the galaxy carries the sun, and Laniakea carries the galaxy, and the ancient light keeps arriving, and none of it disturbs the stillness in which you are hearing this. You are at once perfectly at rest, and travelling faster than any traveller in history. Both are true. Sleep well.